Welcome to Objects in Action, the core concepts powering modern code. In this lesson, we're diving deep into the world of object-oriented programming, unpacking the fundamental concepts that shape modern software. From understanding objects and classes to mastering relationships like inheritance, aggregation, and composition, we'll also explore how functional programming fits into the object-oriented paradigm. By the end, you'll have a clear view of the tools and techniques that drive clean, efficient, and scalable code. Let's get started. When you hear the term object-oriented, it's often followed by words like analysis, design, or programming. These terms are all related to the process of developing software. To create any piece of software, you need to do three main things: understand the problem, plan a solution, and then build it. In other words, it's about analysis, design, and programming, all revolving around the concept of object orientation. In recent years, most popular languages have been object-oriented, but it wasn't always this way. Early languages like COBOL, Pascal, and Fortran were procedural, meaning programs were written as long procedures. Sure, they had functions and subroutines to break things up, but managing large-scale projects in these languages proved difficult. As programs grew, so did the complexity, and it became increasingly hard to maintain them. In object-oriented languages, rather than writing a single long procedure, programs are split into self-contained objects, each representing a part of the application. These objects have their own data and behaviors, and they communicate with each other to solve problems. They represent things like employees, patients, photos, products, bank accounts, cars, or even monsters in a video game. Whatever exists in your application. Object orientation is a programming paradigm, a set of concepts that is supported by many languages. While there are alternatives to object-oriented programming, such as procedural languages like C, logic programming languages like Prolog, or functional languages like Haskell or F#, these are often specialized. For practical, real-world applications like web, mobile, desktop, or game development, object-oriented programming is the standard for building maintainable software with languages like C++, Java, Python, JavaScript, C#, and Ruby. But why is this concept so central? And what exactly is an object in object-oriented programming? In object-oriented programming, everything revolves around objects. But what exactly is an object? An object in object-oriented programming is similar to an object in real life. Think of something like a car or a book. Just like real-life objects, programming objects have three key things: identity, attributes, and behaviors. First, let's talk about identity. Every object is unique with its own identity. For example, if you have two copies of the same book, they're still two separate books or two distinct objects. In programming, each object is distinct, even if it shares the same characteristics with another. Next are attributes. These are the characteristics that describe an object's state. A car might be blue or black. An employee has a name, an ID, and a department. These attributes define the current state of the object, and importantly, the state of one object is independent of others. Finally, objects have behaviors. These are the actions that an object can perform. Just like a car can accelerate or an employee can sign in, objects in programming can perform specific actions depending on their type. So, an object in object-oriented programming is defined by three things: its identity, attributes, and behaviors. In programming, objects are self-contained. They have their own identity, attributes that define their current state, and behaviors, the actions they can perform. But in computer programming, we can take it further. In a computer program, a date could be an object. A bank account could be an object. An event could be an object. Unlike in real life, objects in a program are not just physical things we can touch. They'd also meet the same definition of objects. They have identity, attributes, and behaviors. Let's take that bank account example. One account is distinct from another. That's its identity. It also has attributes, like an account number, holder's name, and balance. These describe its current state. And then it has behaviors like deposit, withdraw, open, and close. So objects in programming aren't always visible or tangible, but they follow the same rules. But where do these objects come from? How do we create them in a program? That's where classes come in. We'll explore those next. You can't talk about objects without mentioning classes. They're inseparable. Classes are used to create objects. Think of a class as a blueprint or a template. It defines what an object will be, but it's not the object itself. The class describes everything about how objects of that class should be created. Once you define a class, you can create any number of objects based on it. A class has a name, also known as its type, and it describes two key things: its attributes and behaviors. In coding, we call these attributes properties and the behaviors methods. For example, if your application deals with banking, you might create a bank account class. The class defines that each bank account object will have attributes like an account number and a balance, but it doesn't specify what those values are, just the structure. In terms of behaviors, the class might define actions like open, close, deposit, and withdraw. Once the class is defined, we can create objects from it. This process is called instantiation, and each object is an instance of the class. Each object has its own identity, data, and behaviors. For example, one bank account object might have a balance of $200, another might have $850, and yet another might be overdrawn at $25. You can deposit to one account and withdraw from another. Each operation is independent. Many object-oriented programming languages provide built-in classes for basic things like strings, dates, or arrays. These classes are part of the language's framework or come packaged with libraries. However, to build applications with custom functionalities, we often need to write our own classes. Writing good classes is essential for maintainable, scalable software, and there are several principles that guide us in doing that well. In object-oriented programming, four key principles form the foundation of how objects interact, evolve, and work together to solve problems. These are often referred to as the four pillars of OOP: abstraction, encapsulation, inheritance, and polymorphism. Each of these plays a crucial role in helping us write more maintainable and reusable software. Over the next few slides, we'll break down these pillars one by one, explore how they work, and see how they help us design better software. Let's dive into the first of the four pillars of object-oriented programming: abstraction. In everyday life, we're surrounded by abstraction. Think about your car. You don't need to know how the engine works to drive it. You just need to know the basics: steering, accelerating, braking. The complex inner workings are hidden from you, and you only interact with the essential parts that you need. That's abstraction. In programming, abstraction works in the same way. It's about hiding complexity and exposing only what's necessary. When you interact with an object, like a bank account object, you don't need to know all the internal code behind it. You just need to know how to perform essential tasks like depositing money, checking the balance, or withdrawing. The rest, the complex logic that makes it all work, stays hidden. By abstracting details, we simplify interactions and make our code easier to manage, understand, and change. Abstraction allows us to focus on what an object does rather than how it does it, reducing the complexity of the code we interact with. This not only improves clarity, but also reduces the impact of change. When internal implementations evolve, the overall system is shielded from these changes. Because other parts of the program only rely on the abstract interface, we can modify the hidden complexities without affecting the rest of the code. This makes the code base more adaptable, scalable, and easier to maintain in the long run. So, abstraction helps us focus on what matters, while the complexity stays under the hood. Now, let's move on to the second pillar of object-oriented programming: encapsulation. Encapsulation is the concept of bundling data and methods that operate on that data into a single unit known as an object. But it's not just about grouping things together. It's also about protecting that data from unintended interference by restricting access to it from the outside world. This is known as information hiding. The idea is that an object should not reveal anything about itself except what is absolutely necessary for the other parts of the application to work. For example, in the bank account class, we don't want other parts of the application to directly change the balance of any object without going through the deposit or withdraw methods. These methods might include important actions like auditing or logging each transaction. By hiding the balance attribute and restricting direct access to it, we ensure that only the class's own methods can modify it. Other parts of the application can still update the balance, but only by going through deposit and withdraw, ensuring that the balance is protected from arbitrary modifications. This is the essence of encapsulation. Objects expose a public interface, what you can do with them, while keeping their internal data hidden and safe from external modification. In programming, encapsulation is typically achieved by declaring variables as private so they can't be accessed directly from outside the class. To give controlled access to these variables, we create public methods, usually getters and setters, that allow reading or modifying the data in a safe manner. For example, in the bank account class, the balance variable would be marked private, meaning it can only be accessed or modified from within the class. We can provide a getter method to allow other parts of the application to read the balance, but prevent them from changing it directly. Instead, they must use the deposit and withdraw methods, which might also include important logic like validation, logging, or auditing. Encapsulation improves code integrity by protecting internal data from unintended changes. It also enhances flexibility, allowing internal changes without breaking external code, and helps reduce bugs by ensuring controlled access to key data. Now let's move on to the third pillar of object-oriented programming, inheritance. This concept is all about reusing and building on existing code. Inheritance allows us to define a new class based on an existing one, inheriting its attributes and behaviors while adding or modifying features to suit new needs. A new class, called the subclass or derived class, inherits attributes and methods from a parent class or base class. This helps us avoid code duplication, improving the readability, extensibility, and maintainability of our programs. For example, imagine you've already defined a vehicle class with common attributes like speed and fuel capacity and behaviors like start, stop, accelerate, and brake. Now, if you wanted to create a car class, you wouldn't need to rewrite all that functionality. The car class can inherit everything from vehicle, and then you can add specific details like the number of doors or air conditioning. With inheritance, we can create a hierarchy of classes that models real-world relationships while keeping the code clean and efficient. It also makes our programs more scalable and adaptable. If you later need to create a truck or motorcycle class, they too can inherit from vehicle, sharing the common functionality while adding their own specifics. This makes maintaining and extending code easier and more flexible. In essence, inheritance enables us to define general features once and reuse them across multiple classes, promoting code reuse and organization. We can also override behaviors, allowing subclasses to refine or replace functionality inherited from their parent classes. Now let's dive into the final pillar of object-oriented programming, polymorphism. While the term might sound complex, the concept is simple and incredibly powerful. Polymorphism literally means many forms, and in programming, it allows different objects to be accessed through the same interface, but each providing its own specific behavior. Imagine this scenario. You're building a ride-sharing application. You have different types of vehicles, like cars, trucks, and motorcycles, all inheriting from a base class called vehicle. They all share basic attributes like speed and fuel type, and actions like start, stop, drive, and brake. But each vehicle type needs a more specialized version of some of these behaviors. For instance, a car might drive with two-wheel power, a truck with four-wheel power, and a motorcycle needs to balance on two wheels while driving. So, the drive method should be implemented accordingly. This is called method overriding, where a subclass provides its own version of a method defined in its superclass. Now, imagine in a procedural programming style, you had to call the drive method for each vehicle type. You need to write a series of conditions using if or switch statements, checking the type of vehicle, and then calling the appropriate drive method. This works for a few vehicle types, but as your application grows and you add more vehicles, you'll need to keep adding conditions, making your code harder to maintain and scale. In object-oriented programming, polymorphism helps us avoid the complexity of using multiple conditions to determine object types. Instead of writing separate conditions to determine the vehicle type and then execute its implementation of the drive method, you can simply call the same drive method on each object in an array of vehicle objects, without needing to know what class each object was instantiated from, whether it's a car, truck, or motorcycle. The correct version of the drive method is automatically called for each object, simplifying your code, making it cleaner, more readable, and easier to extend. When you are looping through different types of vehicle objects, each one runs its own version of the drive method. This is polymorphism in action. You can treat all vehicles as instances of the same base class, but each behaves according to its specific type. Best of all, when you need to add a new vehicle type, say a bus, you don't need to modify the existing logic in your code. Simply create a new class that inherits from vehicle and override the drive method. Polymorphism ensures that your code stays flexible and scalable as your program evolves. Polymorphism offers a number of valuable benefits in object-oriented programming. First, it simplifies your code by removing the need for conditional logic, making your code more maintainable as it grows. Second, it enhances extensibility. You can easily add new types or behaviors, like a bus or any other vehicle, without having to modify the existing logic. Finally, it promotes reusability. The same code can handle multiple object types, even if each behaves differently. This keeps your code base clean, flexible, and scalable as your program expands. At the core of every object's lifecycle in OOP are two key concepts: the constructor and the destructor. When an object is created, the constructor is the first method that runs, allowing us to initialize the object with specific values or set up any necessary configurations. In many cases, we can provide multiple constructors, sometimes known as overloads, that allow the same class to be initialized in different ways, depending on what data we have at hand. For example, if we're creating a vehicle object, one constructor might accept the make and model, while another could also accept the year and color. This flexibility lets us ensure that our objects are properly set up for their intended use. At the end of an object's life cycle, a destructor comes into play. Destructors, also known as finalizers, are responsible for releasing resources or cleaning up when an object is no longer needed. However, unlike constructors, destructors aren't invoked directly by the programmer. Instead, they're automatically called by the garbage collector when the system determines that an object is ready to be removed from memory. It's worth noting that in modern programming, especially with managed languages like C# and Java, explicit destructors are rarely used. These languages provide garbage collection, which handles most of the memory management automatically. That said, when you're dealing with unmanaged resources, like file handles or network connections, implementing an iDisposable interface or its equivalent is crucial. This lets you manually release resources in a timely manner, keeping your applications efficient and resource-friendly. Static, shared, or class-level members. In object orientation, some data or behaviors are shared by all instances of a class rather than being unique to each object. Think of a saving account class where every account should have the same interest rate. Instead of storing this rate separately in every single instance, we can use a static variable. This way, the interest rate is shared among all accounts, making it easy to adjust or reference without duplication. In practical terms, a static member means you don't need to create an instance of the class to access it. It's shared across all objects of the class. In object-oriented programming, understanding the relationships between objects is crucial for building flexible and maintainable systems. Beyond the four pillars of OOP, concepts like association, aggregation, composition, and the principle of composition over inheritance help us model real-world interactions more effectively. These concepts guide how objects work together and emphasize reusability and robustness in software design. Let's dive into these advanced OOP techniques to see how they can elevate our approach to structuring code. Let's start by exploring object relationships with the concept of inheritance. Inheritance describes and is a relationship, and it's not a technical term. It's plain, everyday language. Think about it. A car is a vehicle, right? Or a truck is a vehicle. That makes perfect sense. But what about this? A card is a truck. That doesn't sound right, does it? We naturally understand these relationships. Inheritance in programming builds on this idea, helping us define logical relationships between objects based on what makes sense. But inheritance doesn't just stop there. It can go deeper, creating multiple levels of inheritance. Think about this. A Persian is a cat is a mammal, and a mammal is an animal. This shows a chain of inheritance, where each level inherits properties and behaviors from the one above it. Just as every cat is an animal, in programming, subclasses can inherit not only from their immediate parent, but from multiple levels up in the hierarchy. This is key in building complex, reusable structures where classes at every level share common traits, but also have unique characteristics. When a subclass inherits from its parent, it automatically receives the parent's attributes and behaviors. So, car, truck, and motorcycle inherit everything from the vehicle class. Then we can add extra attributes and behaviors specific to the subclasses. Sometimes, a subclass may need to modify how certain inherited behaviors work. Let's say the vehicle class has a drive method, but we want some subclasses to handle driving differently. The car class might override the drive method to include two-wheel drive, while the truck class could need to implement a multi-axle drive system. This is called overriding. This gives us flexibility to customize behaviors in each child class without changing the base class. Now, what if you have a class that is never meant to be instantiated directly? For example, we might only want to create instances of car, truck, or motorcycle, but never a vehicle itself. In that case, we could make the vehicle class an abstract class. Abstract classes are used purely for inheritance and are never instantiated directly. They provide a framework for other classes to build upon. Languages like C# and Java allow us to explicitly mark a class as abstract, ensuring it can't be instantiated. Inheritance allows us to build flexible, organized, and reusable code. We can share common behaviors in a base class while allowing specialized behaviors in child classes, all through the simple, powerful idea of the is-a relationship. Inheritance offers some powerful benefits for your code. By promoting code reuse, you avoid duplication, which simplifies your code base. This not only saves time, but also makes your code easier to maintain. Plus, with inheritance, extending your applications becomes a breeze, as new functionality can be built upon existing structures. Inheritance usually involves sharing attributes and methods between classes in a parent-child relationship, but there's another form of inheritance called an interface. An interface is like a blueprint, but it contains no actual implementation, only a list of method signatures. It's essentially a contract. When a class implements an interface, it's making a promise to define those methods with the exact signatures provided in the interface. Interfaces offer several key benefits to your code design. First, they promote loose coupling by allowing different classes to implement the same interface, which lets you swap objects without changing the code that uses them. In this example, we see how interfaces enable flexibility by defining a contract for behavior without tying it to specific implementations. We start by defining an drivable interface, which outlines two methods, start and stop. Notice there's no actual code within the interface, just the method signatures. Next, we implement this interface in both a car class and a motorcycle class. Each class provides its own specific implementation for these start and stop behaviors, fulfilling the contract set by the interface. In Vehicle Manager, we use the interface to treat both the car and motorcycle objects in the same way. This flexibility improves the extensibility of your code, making it easier to add new functionalities. Additionally, interfaces enhance testability because you can mock or substitute different implementations during testing without altering the underlying code. Ultimately, interfaces help maintain clean, modular, and easily maintainable code. There's a well-known design principle: program to an interface, not an implementation. This means your code becomes more flexible, extensible, and easier to maintain because you're specifying the behavior that a class must support without dictating the internal workings. In object-oriented programming, we can categorize relationships between objects into several forms. At the core of these relationships is association. Association simply means one object knows about or interacts with another object. It could be as simple as one object calling a method in another. For example, a doctor treats multiple patients, or a library has books available for lending, or a customer uses a shopping cart that contains items. But we can dig deeper into two specialized types of associations: aggregation and composition, which describe how objects relate in a more specific way. First, let's look at aggregation. Aggregation is when one object is made up of other objects, but those objects can exist independently. This is commonly referred to as a has-a relationship, in contrast to the is-a relationship we saw with inheritance. For example, a customer has an address, or a car has an engine. It's important to note that has-a can also mean has many, such as a bank has many bank accounts, or a school has many students. In aggregation, the contained objects are independent. Let's say a classroom object contains an array of student objects. If the classroom object is destroyed, the student objects still exist and could be used elsewhere, such as in another classroom. Now let's move to composition, a more specific form of aggregation. Composition also describes a has-a relationship, but with a key difference: ownership. In composition, when the container object is destroyed, all its contained objects are destroyed with it. For instance, think of a document object and a page object. A document is composed of pages. If you delete the document, the pages are deleted as well, because the pages are owned by the document. That's the key distinction. In aggregation, the contained objects can live independently of the container object. In composition, the contained objects are owned, and when the owner is deleted, they are deleted too. Now let's dive into an important principle often discussed in software design: composition over inheritance. You may have heard about it, but what does it really mean, and when should we apply it? Inheritance, as we've seen, is a powerful tool for sharing behaviors and attributes between classes. But sometimes it can make our code less flexible or harder to maintain, especially when classes become tightly coupled. This is where composition comes into play, offering a more modular, flexible approach. Instead of inheriting from a base class, we can compose an object with other objects that provide the necessary behavior. Think about this. Inheritance describes an is-a relationship, while composition says an object has a particular functionality without rigid hierarchies. One of the biggest advantages of using composition over inheritance is flexibility. With composition, you can mix and match behaviors at runtime, allowing objects to evolve without needing to change class hierarchies. Composition encourages modular design by breaking down behaviors into smaller, focused components, each with a single responsibility. You create a more maintainable and understandable codebase. This modular approach also allows different parts of your application to remain loosely coupled, making the system easier to modify and extend. Reusability is another key advantage. Since behaviors are encapsulated in separate classes, you can reuse them across different objects and scenarios without duplicating code, keeping your code base lean and efficient. For instance, imagine we're designing a game. You have unique characters like Aqua Warrior, a master of the seas who can both swim and fight, and Sky Knight, soaring through the skies and battling foes. At first, you might think each character should inherit abilities like swimming, flying, or fighting from a common base class. But here's the challenge. Should every character inherit abilities they don't even use? For example, should Aqua Warrior inherit flying, even though it never takes to the skies? Instead of cramming everything into a rigid inheritance chain, composition offers a better approach. With composition, we can compose these abilities separately and add them to each character as needed. Each hero gains their abilities through composition, not inheritance. Instead of inheriting behavior from a parent class, we inject flying, swimming, and fighting abilities into each character, giving us maximum flexibility. Need to add a new ability, like healing? No need to touch the existing class structure, just create a class with healing behavior and plug it into any character. With composition, extending or modifying behaviors becomes simple and scalable, keeping our code clean and adaptable. Here, we define interfaces for those behaviors like fly, fight, and swim, and provide their implementations. Each character, like Aqua Warrior and Sky Knight, receives the appropriate abilities by injecting these behaviors through their constructors. We've now explored the core principles of object-oriented programming: abstraction, encapsulation, inheritance, and polymorphism, which have helped us build flexible, modular, and maintainable systems. But modern programming isn't just about one paradigm. Over time, many object-oriented languages, like C#, Java, and Python, have begun to embrace another powerful paradigm: functional programming. Functional programming focuses on pure, stateless functions, immutability, and treating functions as first-class citizens. By integrating these functional programming principles into object-oriented code, we can write more modular, concise, and predictable code that leverages the best of both worlds. In this section, we'll dive into functional programming paradigms in OOP and explore how concepts like first-class functions, higher-order functions, and immutability are making OOP more powerful and expressive. Now, let's begin by exploring one of the key principles of functional programming, first-class functions, and how they empower us to write cleaner, more flexible code within object-oriented languages. We'll also see how this leads to the concept of higher-order functions, which allow us to treat functions as data, passing them around just like variables. These terms might sound complex, but the ideas behind them are straightforward and very powerful. First-class functions simply mean that functions are treated just like any other value in the language. You can pass them as arguments to other functions, return them from functions, and assign them to variables. This allows us to dynamically decide which behavior to apply based on the situation, leading to more concise and modular code. Then we have higher-order functions, which are functions that can take other functions as arguments or return functions. For instance, we can write a function that processes each element in a list by applying another function to it. This allows us to define generic behavior that we can customize by simply passing different functions. This flexibility allows us to decide at runtime what action to perform on the elements, whether it's doubling, squaring, or any other operation. Higher order functions opens up powerful patterns like callbacks, function composition, and even functional utilities like map, filter, and reduce in functional programming. You may not realize it, but many of the constructs we use in modern OOP languages like C# or JavaScript, such as delegates, lambda expressions, and event handlers, are rooted in these functional programming principles. For instance, in C#, you can pass a function to a list's where method to filter elements, or to the forEach method to apply an action to each item in the list. These features make it easier to build programs that are more modular, testable, and adaptable. OOP languages have embraced these patterns because they make code more expressive and easier to reason about, especially as applications grow in complexity. Now let's explore two powerful concepts from functional programming that are making their way into modern OOP: immutability and pure functions. These ideas might seem abstract at first, but they're crucial for writing more predictable, testable, and bug-resistant code. Let's start with immutability. In simple terms, immutability means once an object is created, it can't be changed. Instead of modifying data, you create new objects with updated values. This might sound inefficient at first, but in some cases it actually helps prevent a lot of tricky bugs that come from unexpected changes to shared data. Imagine a transaction object in a financial application. Once a transaction occurs, whether it's a deposit, withdrawal, or transfer, the details of that transaction never change. By keeping transactions immutable, you ensure that no part of the program can accidentally or intentionally alter the transaction objects, making your data more reliable and secure. Next, let's talk about pure functions. A pure function is one that, given the same inputs, will always produce the same output and it doesn't cause any side effects, meaning it doesn't change anything outside of itself, like changing global variables or modifying objects outside its scope. Pure functions make your code easier to understand, debug, and test as they are completely predictable. If you pass in the same input, you'll always get the same output, and you don't have to worry about hidden changes happening elsewhere in your application. In this example, the calculate balance function processes a list of transactions to compute the total balance. The function is pure because it relies solely on its input, the list of transactions, without modifying any external state or data. It consistently returns the same output for the same input, ensuring reliability and predictability in the calculation of balances. Now, while pure functions and immutability are essential in many cases, there are scenarios where an impure function is more practical. For example, take a look at a bank account object. When you're dealing with something like an account balance, you do need to modify the state. In the real world, when processing a list of transactions, you wouldn't create a new bank account object for every deposit or withdrawal. You'd update the existing balance instead. However, even though this function is impure, we still need to use it responsibly to ensure our code remains predictable and easy to maintain. When you combine immutability and pure functions, you get code that's highly reliable, thread-safe, and easy to reason about. You can track how data flows through your program and be confident that nothing unexpected is happening behind the scenes. These ideas, originally from functional programming, are now being embraced in OOP to make software more maintainable and resilient. Next up in our journey through functional programming paradigms in OOP is functional composition. At first, the term might sound a bit intimidating, but the concept is surprisingly simple and extremely powerful. Functional composition is all about combining simple functions to build more complex operations. Rather than writing one huge complicated function, We break the problem into smaller, manageable pieces. Each piece does one thing, and we can stitch them together to create more advanced functionality. Let's make this even more practical by introducing custom extension methods, a powerful tool in C# for adding functionality to existing types without modifying their source code. This is perfect for demonstrating functional composition in a real-world context. In this example, as we process the dataset, the first two steps, filtering outliers and normalizing values, transform the data. But the final step, calculate metrics, is an aggregation. It takes the clean data and provides a summary, calculating the average and standard deviation. While the first two steps fit into a pipeline of transformations, this last step wraps up the process, providing key insights from the data. Functional composition isn't just a theoretical concept, it's a practical way to make your code cleaner, more modular, and easier to maintain. By breaking down complex tasks into smaller functions, you reduce complexity and improve readability. Each small function can be tested individually, improving your code's reliability. Also, it improves the code reusability as individual functions can be reused in different pipelines. And best of all, by chaining these functions together, you keep your code flexible and easy to update as requirements change. Now, let's talk about how two different programming paradigms manage access to data: closures in functional programming and encapsulation in OOP. Although these two paradigms seem different, closures in functional programming share a common goal with encapsulation in OOP. Both aim to control how data is accessed and modified. Let's start with closures. In functional programming, a closure is a function that retains access to the variables from its surrounding scope, even after that scope has exited. In simpler terms, a closure remembers the environment it was created in and can use those variables long after the original context is gone. Imagine we're building a simple counter. Normally, you would expect the count variable to be reset after the function finishes, right? But closures work differently. Let's see how it works in code. In this case, the createCounter function returns a closure, a function that retains access to the count variable. Each time we call counter, it remembers the value of count from the previous execution. This encapsulates the count variable, making it inaccessible to any other part of the program. In object-oriented programming, encapsulation bundles data and methods inside an object. You use access modifiers like private or getters, setters to control what can be accessed or modified from the outside world. Both closures and encapsulation share a similar purpose. They protect internal state by providing controlled access. While closures trap variables inside functions, OOP encapsulates data inside objects, providing access through well-defined methods. So, whether you're encapsulating a variable inside a function with a closure or controlling access to object data with OOP, both techniques aim to manage how data is accessed and used. Both closures and encapsulation lead to cleaner, more maintainable code by ensuring that data is only accessed or modified in the ways you've explicitly defined. By limiting access to internal states, you reduce the risk of unintended side effects, making your code safer and more predictable. Now we've explored functional programming concepts, let's dive into an important distinction: declarative versus imperative programming. These are two different ways of thinking about how we write code, and you'll find elements of both in modern object-oriented programming. In the imperative style, you're telling the program how to do something, step by step. It's like giving detailed driving directions. You specify every turn, every signal, and every street to follow. For example, let's say we want to find all even numbers in a list of integers. In an imperative approach, you write a loop and check each number individually. This is a typical imperative style in object-oriented programming, where you instruct each step the program must take. On the other hand, the declarative style focuses on what you want to achieve without worrying about how it's done. It's more like giving an end goal, find all the even numbers, and letting the system figure out the steps. In the same task, using a declarative approach, you might use LINQ and C# to express what you want more clearly, like this. Here, you simply declare what you're interested in, numbers that are even. The internal logic of how it filters is abstracted away. Even though OOP languages are typically imperative, you can still adopt a declarative approach in many cases, like using higher order functions such as where select or aggregate. This allows for more concise and readable code. So, why does this distinction matter? Declarative programming helps you write code that's easier to reason about and maintain. You're focused on the result, not the process. On the other hand, imperative programming gives you more control over the fine details. Understanding when to use each style helps you become a more versatile programmer. In object-oriented programming, learning to balance imperative and declarative styles can lead to more readable, maintainable, and expressive code. It's about finding the right tool for the job. By combining the best of both object-oriented programming and functional programming, developers get the advantage of structure and flexibility. The traditional OOP structure organizes your data and behaviors into clean, reusable objects, but by incorporating functional techniques, we make our code even more powerful. For instance, code readability improves by reducing the number of nested loops and control flows. With declarative approaches like functional composition, you clearly see what the program does, rather than how it does it. Additionally, maintainability is improved. Pure functions, once implemented, reduce the likelihood of introducing bugs. No matter how your application evolves, the immutability of objects ensures that you can build upon your program with fewer risks of unexpected side effects. Blending these paradigms also enhances reusability. Functional techniques like first-class functions and higher-order functions allow us to create more generic solutions that work across different use cases. And when it comes to testing, pure functions shine. Since their output depends only on their input and they don't modify any external state, they're easier to isolate and test. Finally, in modern applications, concurrency and parallelism are increasingly important. Functional programming's emphasis on immutability makes handling concurrent tasks much safer and easier to manage. As we wrap up this journey through object-oriented programming, let's take a moment to reflect on the core concepts we've covered that empower modern code. We began with an introduction to OOP, where we explored the core characteristics of objects, identity, attributes, and behaviors, and saw how classes define them. Next, we dove deep into the four pillars of OOP: abstraction, encapsulation, inheritance, and polymorphism, the foundation of object-oriented design. Then, we uncovered the inner workings of objects and classes, learning about object lifetime through constructors and destructors, and understanding the role of static or shared members that exist at the class level. In mastering object relationships, we explored inheritance and how it enables and is a relationship, followed by association, aggregation, and composition, where we saw the different ways objects interact. We capped it off with composition over inheritance, showing how flexibility is often found in composition-based designs. Our journey took a functional turn as we explored functional programming paradigms in OOP, starting with first-class functions and higher-order functions, leading us through immutability and pure functions that promote safer, predictable code. We saw how functional composition builds complex functionality from simple pieces and how closures enable encapsulation within functions. We compared the declarative and imperative styles in OOP, and finally saw the benefits of blending functional programming with OOP to unlock even more power and flexibility. By mastering these core concepts, you now have the tools to build cleaner, more modular, and scalable code. Thank you for watching and being part of this journey into object-oriented programming. If you found this video helpful, please give it a like and consider subscribing for more content like this. Don't forget to hit the bell icon so you never miss an update. Keep coding, and we'll see you in the next video.